Look at all this stuff for derivatives. And you thought it was just a little tiny little tangent line, huh? You thought it was just a pretty little tangent line. Look what it's delivered so far. Some very, very nice, timeless ideas. And guess what we're doing today? We're adding a sixth one on there. So, for the sixth idea for derivatives, we're going to need a couple ingredients. Some very, very easy ingredients. Here's the first one. The first ingredient is that you have to be good with your plug-in skills. Wow, what does that mean? Well, don't worry, you're in good hands. To be good with your plug-in skills, what I mean by that is that you should be able to do this problem. Say, suppose I give you that A is equal to 3. Suppose I give you that K is equal to 1. And suppose I give you that X is equal to 2. And suppose I give you that 7, well, no, 7 is equal to 7. X is equal to 2. And suppose I tell you solve for B. Well, this is ridiculously easy for a student, a typical student in this class. We've done so much algebra here. This is child's play. What you would do is you plug that in there. A is equal to 3, so you got 3. K is equal to 1, so you got 3 times 1 plus B is unknown. That's the one we got to solve for. X is 2, and that's equal to 7 times 3 again. So that means that 3 plus 2B is equal to 21. That means that 2B is equal to 18. And that means that B is equal to 9. See how easy that is? I make this stuff look easy, huh? That's why they pay me insane amounts of money. So, first and key ingredient for today's lesson. Today's lesson is going to be number 6 on this list. First key ingredient is you've got to be down with the plug-in stuff. It's got to be really, really easy. All you do is plug things in there. Of course, they won't look like this. What they'll have is some other calculus-y looking things in there. But the skills are exactly the same. Suppose in this case I tell you that A is equal to 0, X is equal to 3, dp dt is equal to 7, K is equal to 1, and I tell you solve for dr dt. Well, child's play. By this point you should almost be angry at the insult to your intelligence. This is really, really easy. For a typical student in this class, you've done so much algebra. This is nothing. Here you plug things in there. A is equal to 0, so you got 0 times 3 squared times 7 plus 4 times 1 times dr dt is equal to 5. So this goes away, that's 0. So you have that 4 dr dt is equal to 5. So then that means that your dr dt must be equal to 5 over 4. I know someone's going to be thinking, how did he get that? How did he get 5 over 4? Well, I divided both sides by 4. I divided this side by 4 and I divided that side by 4. Or I multiply both sides by 4th if you want. Anyways, I won't do any more. I won't torture you anymore with these examples, but you've got to be really, really good with your plug-in skills, okay? There's nothing calculus-y about this other than the way the symbols look. All you're doing is plugging things in there and solving algebraically as you would have done maybe in an algebra class many, many moons ago. Clear? You guys got it? Or you need like 20 more examples of this? Hey, do you guys remember when you used to think this was hard, this was difficult in your algebra class? Or junior high school class or whatever? You used to think, whoa, that is so difficult. Yeah, it always looks that way after a while. Alright, okay, then this is a different ingredient. This is not the plug-in. This ingredient is, hey, you gotta be good with your DDT skills. DDT skills. What exactly do I mean by that? You have to be good at slapping a DDT on both sides, or you know, a more traditional calculus teacher may say you have to be good at taking the derivative of each of the expressions with respect to t. I say slap a DDT on both sides, slap one on this side, slap one on this side, DDT on that side. If these two functions are equal, then their derivatives with respect to t should also be equal. Oh, and then you get a chance to practice all your excellent derivative skills. Remember? For example, what's the derivative of e to the stuff? Well, that would be e to the stuff times the derivative of the stuff. Right? Let me make that look good, because that's not the kind of teacher I am. That would be the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Okay, let's do the left hand side now. The derivative of the sum, well, that would be the sum of the derivatives, so I have to do each piece separately. Forget about that one for a second. Let's just handle this. This is the derivative of a product, so that would be the derivative of the first one, d dt of x times the other thing, plus the first one times the derivative of the second one. That right there, that's called product rule. Super famous. And then here I could pull the constant out. All I have is 5 times the derivative of that. Let me think. That would be 5 times the derivative. I'll just take baby steps here. Of ln of stuff. Okay, then you could take a break if you want. Go get some tea, water, whatever. Salud. And then you gotta take the derivative of this. Alright, let's see how this goes. The derivative of x with respect to t, well, that would be just dx dt plus x, the derivative of stuff squared. Well, that would be 2 times this stuff. You bring the 2 down, you subtract 1 from the exponent, and then you have to do dy dt. Okay? That's 2 stuff, take 1 away, and then derivative of the stuff. That's called chain rule. Super famous. 5, the derivative of ln of stuff. Well, that would be 1 over the stuff times the derivative of the stuff. And that would be equal to e to the y dy dt. There it is. Very easy. Or, you know, again, you should have done so much homework where this stuff is really easy. There's not much going on here. You just take the derivative using chain rule with respect to t. And so that's it. Those are your 2 key ingredients. All you need is 2 today. Super easy. This is going to be like a 5-minute lecture. No, I'm kidding. It's probably been more than 5 minutes already. It's been 8 and some change. So, but the point is, it's going to be a really straightforward lecture, but deep. All you need is two ingredients. You need your plug-in skills, plugging things in and solving, and you need your DDT skills, being able to slap a DDT on both sides and doing the derivatives correctly. That's it. 2 simple ingredients. However, something really nice happens when you apply these 2 skills to some classical problems. Take this one, for example. This is a classical formula. You may see it as something familiar. You may think, oh, I've seen that before. Where have you seen that before? A is equal to pi r squared. Of course, that's the area of a circle. If this is r, then the area is equal to pi times r squared. By the way, you should ask why. Why is that? You should be able to prove why. Anyways, something amazingly happens when you apply these 2 key ingredients to classical formulas, such as this. In fact, to any formula, anytime you know how 2 things are related. In this case, I know how the area is related to the radius. They are related by this formula. And the big idea for today's lesson is the fact that every time you know how 2 variables are related, you know how their related rates are related by just slapping a DDT on both sides. Yeah, that means nothing. Let me actually do it so you'll see. Slap a DDT. That was one of our crucial skills. Slap a DDT, and that was another one of our crucial skills. Slap a DDT on both sides. Okay, that was the same skill. You get that dA dt is equal to, let me think, this would be pi times 2 times r. And that would be fine if it was ddr, but it's not, so I got to do chain rule dr dt. Okay, brought the 2 down, subtract 1, the derivative of the stuff. Super, super famous. Something happens when you apply our 2 key ingredients today to classical formulas like this. This is telling you the classical interpretation of t is time. This is telling you that the rate at which a, if you have, these are slopes, the rate at which a changes, this is rise over run. How much does area change compared to time? The rate at which the area changes is equal to 2 times pi times r times the rate at which the radius changes. What the hell does that mean? It's tough. I know it's tough. Again, let me say it again. The rate at which the area changes is equal to 2 times pi times r times the rate at which the radius changes. What does that mean? I'm just kidding. It means something classical. It means, for example, suppose you had something like this. You had a circle here, and suppose inside the circle you had fire, a lot of fire. This is fire. It's burning. And as this circle is a circular shape is burning, suppose that the radius is expanding. This is the radius, and the dr dt, that would be the rate at which the radius is expanding. Suppose you've got an empty field, a huge field, and you got a fire, and it keeps growing and growing and growing and growing. Suppose it's growing, for example, at 2 miles per hour. So this would be a big concern for, say, the firemen or people around it. Hey, it's growing at 2 miles per hour. Then there comes a super, super interesting question. If the circle is expanding at, the radius is changing at 2 miles per hour, how fast is the area changing? That's an interesting question, because it's not, the area is not changing at 2 miles per hour. No, every single time you add 2 miles here, you add a big ring around there. And the next one, you add a bigger, even bigger ring. So at every single moment, the area is changing at a different rate, because every single little increment on the radius increases the area by a lot more as you get further and further into larger radii. Does that make sense? Here, here's a classical question for us. Classical question is, how fast is the area changing if we know that the radius is expanding at 2 miles an hour? And again, let me illustrate the nuances of the problem. See, suppose that this was the time, say this was after 1 hour, you got 2 miles. After another hour, you got another 2 miles. So this is from 4 miles to 6 miles. In other words, this was hour number 1. This was hour number 2. This was hour number 3. Third hour. At the third hour, it expanded from 4 mile radius to 6 mile radius. So you've got a big ring here that's roughly 2 miles, and it goes around this 4 mile radius band or circle. Compare that with, say, the 10th hour or something like that. After the 10th hour, this would be 2, 4, 6, whatever. You may be going from 18 miles to 20 miles in radius, and this little strip goes around much, much, much further. Even though it's the same width as this one, they're both 2 miles, because that's how much it changes in an hour. From this hour to that hour, 2 miles. These 2 miles are not the same as those 2 miles. They don't have the same area. You see? So as you compare this question, how fast is the area changing as the radius changes? Well, the area is changing, the rate at which it's changing is increasing as you increase the radius. And that sounds really, really complicated. But this idea makes child's play out of it. This tells you exactly how fast the area is changing. It says the area is changing at 2 times pi times whatever the radius is times however fast the radius is changing. Oh, it's beautiful when you see it that way. It takes all the complications out of it just by slapping a ddt on it. The bigger concept behind that is that every time you've got an equation, whatever the equation may be, x squared is equal to 3y squared x. If you know how x and y are related, slapping a ddt on both sides tells you how the rates are related, how the respective rates are related. That right there, that's the key to today's lesson. It's so simple. I told you the 2 ingredients, they seemed like a joke at the beginning, slapping a ddt on both sides and plugging things in. So simple. Yet the complexities are the problems that it addresses are immense, I think. Or they're fascinating. I find it interesting how slapping a DDT on both sides could make such a difficult problem to think about. It's so easy. Well, as long as I have fun, that's what counts, right? I'm just kidding. I hope you like it too. I really do. Okay. So let's do this problem, okay? So suppose I give you something like this. Suppose we're given more information. Suppose when the radius is equal to 7 miles at this point, when the radius is equal to 7 miles, and you know that dr dt is equal to 2 miles per hour, and then you can answer solve how fast is the area changing. Well, that's where your other skills come in, the famous plug-in skills, the difficult algebraic plug-in skills. I'm just kidding, this is not difficult, this is just plugging in there, man. This is the easiest thing in the world. We already did it at the beginning. Okay, so I gotta solve for dA dt. So I got dA dt, that's the one I don't know. I gotta plug everything in there. 2 times pi times the radius, which would be, no, this radius is 7 miles, times 7 miles. Look at the units too, they work out so nicely. Times the rate at which the radius changes, that's 2 miles per hour. Oh, it's so beautiful. You get 2 times 2 is 4. 28 pi square miles per hour. That is exactly how fast the area is changing at this point when the radius is 7 miles. Now, just for fun, let's just compare it. Let's do the same problem, but now compare it, suppose, at a different point. Suppose now I want to check when r is equal to 20 miles. Okay, everything else is the same. The dr dt is still changing. The fire is still spreading at 2 miles per hour. And I still want to solve for... Wow, man. I still want to solve for dA dt. Oh, this is duck soup. Child's play. It's so beautiful, I think. I like it a lot. I don't know why I like this so much. It's clean. So dA dt is equal to 2 times pi times the radius, which would be 20 miles, times the rate at which the radius changes. I'm plugging things into here. This is my baby right here. The equation that tells me how the rates are related. That's why it's called related rates. If you ever forget, this section is called related rates because it tells you how the rates are related. Where was I? 2 miles per hour. What is that? 2 times 2 is 4, times 2 is 8, another 0, 80 pi square miles per hour. You see, the area is changing much faster. You're getting into a lot more burning, a lot more trouble as you let that circle expand bigger and bigger and bigger. Beautiful, classical. I don't know what else to say about it. I think we should pause this and then hit up some more classical related rate problems. How does that sound to you? Good? Alright, so now we got ourselves a classical problem. We got a snowball. And the snowball is rolling down the mountain. As it rolls down the mountain, it keeps getting bigger and bigger and bigger because it collects more and more snow. And then we got a simple but classical problem. Suppose that the volume is... How fast is the volume changing if the radius is expanding at 2 inches per second? That's the question. How fast is the volume changing when the radius is expanding at 2 miles per second? It's a nice question. Again, the same phenomena. When the ball is little, when the snowball is little, expanding 2 little inches doesn't do much. But if the ball is huge, expanding just 2 inches covers a lot more volume. And so the rate at which it's changing depends on how big the ball is, as well as on how fast the radius is expanding. That sounds really complicated, but we make child's play out of that problem using the ideas of I don't know, some guy named Sir Isaac Newton. The ideas of the derivative, Leibniz too. I don't know, I'm kind of partial towards Newton, but a lot of people like Leibniz too. Alright, so here's how we would do it. We've got no business finding how the related rates between volume and radius are related if we don't even know how the volume and the radius are related. So that would be a good place to start. Let me say that one more time. If you want to know how the rate at which the volume changes compared with the rate at which the radius is changing, you better know how the volume is related to the radius, even before they do any changing. Here's how they're related. Volume is equal to 4/3 pi r cubed. Everybody knows that one. By the way, you should ask why. Why is that? Where did it come from? Why 4/3? Why not 5/7 or why not 5/4 or why not 3/2? What the hell did the 4/3 come from? It's a fascinating question. I absolutely love that question. But so many questions, so little time. I gotta let that slide for now. Anyways, this is exactly how the V and the R are related before they even do any changing. Before their rates are changing. How do I make the rates change? Oh, it's so easy. All I do is slap something magical on both sides. I slap a d dt on this side. And guess what I slap on the other side? d dt as well. Oh, this is child's play. This tells me that the rate at which the volume is changing is equal to 3 times 4 divided by 3. That would be 4 pi times r squared. That would be good if you're a beginner, but we're not beginners. We are experts. We know that we always gotta do chain rule, so it's just dr dt. Capiche? See, from knowing how the v is related to the r, I know how the dv dt is related to the dr dt. In a simple process that's called slapping the ddt on both sides. Yeah, try to Google that. Slap the DDT on both sides. See if Google knows about it. Alright, now we can use our other skill, the famous plugin skill. So you gotta have some numbers, otherwise we're going nowhere with this. If that's all the information you're given, you can't do anything. But you need to know when. I need to know for what r. So let me give you an r. Suppose r, at the point when r is equal to 10 inches, and of course dr dt is equal to, it's expanding at 2 inches per second. By the way, the snowball could also be melting, and the dr dt would be negative, and that would cause all this thing to be negative, so it would be a negative change of volume. The volume would be decreasing. I just thought I'd throw that in there. So suppose this is the information we're given for this problem. At r is equal to 10 inches and dr dt is equal to that, solve for dv dt. This is a fancy way of saying how fast is the volume changing. Rise over run. How much did the volume rise? How much did the time run? Rise over run. This is a slope. So then we use our excellent plugin skills, and so we get that dv dt. Can you see that? Huh. I wonder if I'm running too small. Well, make your screen bigger. dv dt is equal to 4 times pi times the 10 inches squared. Notice how nice the units work out too. This would be inches squared times dr dt, which was 2 inches per second. That's going to give you a total of, let me think, 10 times 10, that's 100. That would give you 400 pi. Oh, and I had that 2 in there. That'll give you 800 pi cubic inches per second. So you asked me how fast is the volume changing at exactly the point when the radius is 10 inches and the radius is changing at 2 inches per second. Oh, I got that. It's changing at exactly 800 pi cubic inches per second. Yippee-ki-yay. That's why they pay me. Actually, they're not going to pay me anymore. I might make Math Hands for free. Very, very nice classical problem. Classical. If you know how fast the radius is changing, how fast is the volume changing? Okay, you guys want to do one more classical? This is some classical stuff. Timeless. So here's another timeless question. You know, all textbooks have this. Calculus textbooks. You've got an upside down cone like this, and you fill it up with water, and you ask the timeless question. If you pump out the water, suppose you stick a, I don't know, you stick a pipe in here, and you stick the pipe, and you put the pipe over here, and you put the pump here that's throwing out the water, and you make the water go out. If you pump out the water, say at a certain rate, for example 1 liter per second. I use liter because it's easy to convert to the units. The liter is 1,000 cubic centimeters. Everybody knows that. 1 liter per second. The question is, how fast is the water dropping? That means how fast is the height. Suppose I call this Y, or I could call it H. Doesn't matter. I call the big H. I'll call this H naught. But and I call this H. How fast is the H changing? Given that I know how the volume is changing. Here, they're telling you how fast the volume is changing. They're telling you dV dt is equal to 1,000 centimeters cubic per second, and they want you to find how fast is the. This is a good thing to do always. How fast is the H changing? They give you how fast the V changing, and they ask you how fast is the H changing. And they give you some other information that has to do with the shape of the cone, because you know some cones are really, really round and short, and some of them are tall and sort of thin, narrow. You need this information so that you can know the shape of the cone to figure out, because that would definitely influence how fast the height is changing. But the thing I wanted to emphasize here, they give you the dV dt and they want you to find the h dt. Well, you've got no business talking about this d anything if you don't even know how v and h are related. If you don't know how v and h are related, this problem, you can't even get through step 1. So then we use our noodles here and we think, how is the volume related to the height in here, or the radius? Well, that's classical for a cone. Everyone knows that the volume is equal to 1/3 pi r square h. Yeah, everybody knows that. And I could immediately, right, as soon as I figure that out, I could slap a ddt on both sides. And maybe I might, just for fun. But you could also substitute, clean up the problem a little bit using the shape, put in there the information about the shape here. The information here is that r is equal to 1/3 the height. That might be useful to plug into here so that you only have one variable. Unless you like a lot of variables, you'd have to do product rule here, and it could get really interesting, which may not be a bad idea. But for the r, as a matter of fact, I could substitute a third h. That's just a convenience step because it cleans up my equation. Now I know exactly how this is 1/3 times 1/3 times 1/3. I reckon that's 1/27 times pi times h to the third. Yeah, let me write that in a nicer way. Pi over 27 h to the third. This cleans up the relationship. This is exactly how v and h are related. Again, very, very important. Whenever you read the problem, you ask, what are they asking for? Or they're asking what do they give me and what are they asking for? They give me how fast the volume is changing, and they want how fast the height is changing. That's the information you got to abstract from the problem. Once they tell you those two things, then you got to set your mind to finding an equation that tells you how those two things are related. Once you know how the v and the h are related, then it's all downhill from there, because then you do a little slapping on here, a ddt on this side and a ddt on that side, and these derivatives make child's play out of these problems. dv dt is equal to, this is a constant, so it could come out, so this would be pi over 27, and then you just do the derivative of this, 3h squared, and that would be good for a beginner with very low expectations. But for us, we know that you got to bring the 3 down, the h squared, and then you got to do dh dt. As every good chain rule student knows. That was the ddt part. The rest is duck soup, because here comes the hard part, the plug-in part. We're going to plug everything in there. So we're going to need dv dt. That was 1,000. Oh, it's actually negative. 1,000 cubic centimeters per second. Again, I could carry out the units just to illustrate them, but Maybe today I won't. The units will work out very, very, very nicely if you just keep track of them. This will be pi over 27 times 3. Oops, I gotta know at what height, because obviously if your volume is being pumped out at a constant, it will drop much faster as when you go down the bottom, because this will go, it'll get sucked out fast. You'll drop fast. Over here you won't drop that fast, so it most definitely depends on the height. So let's give it an actual number. Just for this example, let's just say that this will be given in the problem at h is equal to 12 centimeters. Okay, that's got to be given. Otherwise, it stays there as a variable. You'll have to say it depends on what height, because it'll be the dh dt will be changing differently depending on the value of h. So let's say it's 12 centimeters. So this would be 3 times 12 squared, and that's times dh dt. And now you just have to solve for this dh dt. But my goodness, this is so easy. All you do is negative 1000, and then I'm going to divide by pi over 27 times 3 times 144, and there's my dh dt. Okay? And if I wanted to, I guess I could figure that out. I'm not that big into answers. I don't really care about answers. I'm a fan of ideas, not a fan of answers, but whatever. Let's do it. Negative 1000. That's negative, I said. Divided by what? Divided by pi times, no. See why I don't like this? You see? Come on. Pi times 3 times 144. And I'm going to take the 27, I'll put it on the top, so I'll close this parentheses. I'll go here, times 27, whatever. Okay, so that's going to give me exactly how fast this is equal to negative 19.89. Negative 19.89 centimeters per second. What this is telling you is that the height is dropping at a height of 19 centimeters. That's about this much per second at that point. Is that nice? Assuming I did the math right. Whatever, it's kind of nice, huh? It's classical. Everybody does this cone and with the water dropping. It could be filling too, and the question could ask, how fast is the height rising? Well, the only difference would be this would be positive. Everything else would be pretty much the same. You first find out how the v and the h are related, then slap a ddt, then you plug in. Okay, you guys got time for one more classical example? Yeah or no? A 20-foot ladder is leaning against a vertical wall. The foot of the ladder is being pulled away from the wall at a constant rate of 2 feet per second. When the bottom of the ladder is exactly 11 feet from the wall, how fast is the top of this ladder slicing down the wall? Say what? Say what? Oh no, they didn't. Let's try to make sense of this. So we've got a let's give it some letters, right? Let's give it some numbers or letters or something. Let's go with blue. So I'll call this this distance, I'll call it x, and this one I'll call it y, and this one I'll call it h, and we'll assume that the wall is upright, and they say that this one is fixed. It's always 20 feet. The ladder's 20 feet long. And they're telling us that some little clown here, is pulling the ladder at a constant rate of 2 feet per whatever. What was it? 2 feet per second. 2 feet per second. Let me read that carefully. The foot of the ladder is being pulled away at a rate of 2 feet per second. So this clown right here is pulling the ladder. As this clown is pulling the ladder while the ladder's falling down. And then they're asking here's a bombshell right here, the bombarded question, when the bottom of the ladder is exactly 11 feet from the wall, How fast is the top of the ladder slicing? Say what? How fast is the top of the ladder slicing? They're asking dy dt. How fast is y changing? And they're giving you dx dt. How fast the x is changing? They're telling you the x dt is 2 feet per second. They're asking you for how fast is y changing. Stop me if I'm lying. That's exactly what it is. So we use our excellent principle here, and that principle is you've got no business talking about related rates between y and x if you don't even know how plane y and plane x are related. So your first goal should be, hey, I gotta figure out how y and x are related. Well, for a ladder like this, that's kind of easy. For a ladder like that, if you have 20 here, you have x here, you have y here, you have a right triangle. Here's how they're related. A little something we call Pythagorean theorem tells you that that's how they're related, right? Well, that was difficult for about half of a second. And then we do our magic. Once we know how x, y, and x are related, what do we do? Let me give you a hint. Slap something on both sides. What are we going to slap on both sides? A ddt on this side and a ddt on that side. That would give me that 2x dx dt plus 2y dy dt is equal to 0. The derivative of a constant with respect to time is 0. And now comes the hard part, the plug-in part. You got to plug stuff in. What are we plugging in? Okay, this guy right here is my dx dt. This guy right here, when the bottom of the ladder is 11. Oh, with the bottom x is equal to 11. That's what they give us. So x is equal to 11. Dx dt is 2 feet per second. Oh man, I gotta figure out y. Holy macaroni! How am I gonna figure out y? They don't tell me in the problem. They only tell you when the bottom of the ladder is 11. Oh, but before I did all this stuff, I knew how, before the red stuff, I knew that x squared plus y squared is equal to 400. So I knew how x and y are related already. So if I know x and I know how they're related, I could figure out y. So I go back to here and I say, okay, that's 11 squared plus y squared. At that point, the x squared is 11 squared plus y squared is equal to 400, giving me y squared plus 121 is equal to 400. So you got y squared is equal to 400. Take away 120. That would give you 280. But then you got to take away one more. You got 280, 279, I reckon. So y is approximately, well, let's pull out our little magic number machine. Let's do a square root of, by the way, let's check that I did that right. 400 minus 121. I don't know why I checked myself. Anyways, got to do the square root of 279. That's approximately 16.70. That goes in there. So y is approximately 16.70. And so I plug all these things here and I solve for dy dt. How fast is the y changing? That's what we wanted to find. So this will be 2 times 11 times 2 plus 2 times 16.70 times dy dt is equal to 0. And this is the one I got to solve for. 2 times 2 is 4. That's 44. I move that over to the other side. 44. So dy dt is equal to negative 44. Oh, nice. The sign is telling me the correct stuff. The y is dropping. All over 2 times 16.70. So here's what we do. We pull out our little calculator here and we go clear everything. You go 44. That's a negative 44. Divided by 2. And whatever you get, you divide it by 16.70. And what do we get? Negative 1.0. I'll round off, negative 1.32. So this is equal to negative 1.32. Nice. So here's a little answer. When you've got a 20-foot ladder leaning against a vertical wall and the bottom of the foot is being pulled by some clown at a rate of 2 feet per second, when the bottom of the ladder is exactly 11 feet from the wall, how fast is the top of the wall slicing down? Well, the top of the ladder is sliding down at negative 1.32 feet per second. Yippee-ki-yay. Told you.